Hello everyone, my name is Xiaohan and I'm from Fudan University. Today we present our work, an empirical study of web resource manipulation in real-world mobile applications. This is a joint work with researchers from Fudan University, Indiana University, Northeastern University, and Tsinghua University. Okay. It is well known that today's mobile applications are integrating more and more web services to achieve functionalities such as advertising, social sharing, and even authentication and authorization. Most of such web and app integrations are through lightweight in-app web browsers called web views, or WebView on Android, and UI WebView or WK WebView on iOS. These web views connect the web platform and the app platform. However, the integration of web and app platforms may bring security risks to both sides, which are called web-to-app attacks and app-to-web attacks, respectively. Most of previous work have been focusing on web-to-app attacks, where unauthorized web code, namely JavaScript code, can access sensitive functions of the host apps. They studied the attack services and they proposed detections and defenses, and so this kind of security risks is well studied. However, few work look the problem from the opposite side, that is app-to-web attacks, where the host app can manipulate sensitive resources of the web. There are some existing works only partially discuss the problem in theory with no real-world cases found. So this kind of security risks is not measured yet. In fact, there are at least two open questions to be answered. First, how web resources are manipulated by real-world apps. And second, are there any real-world app-to-web attacks? This paper, therefore, is proposed to answer these questions. To understand these questions, we first look into web resource manipulation APIs that is provided by mainstream mobile OS. We find that both Android and iOS provide a handful of APIs for the host apps to manipulate web resources, even very sensitive resources such as local storage, web content, web address, and network traffic. For example, the host apps can obtain cookies from any domains using the API countermeasures.getCookie. And they can also intercept network traffic to extract user credentials using should-intercept request. The question here is it secure to use these APIs? Let's see a motivating example to understand the problem. On the right, we can see that the website facebook.com is loaded into web views of two different apps, app A and app B. And both these apps use countermeasures.getCookie to obtain cookies from facebook.com. The fact is that app A is actually Facebook's official app, while app B is called ChatOS. It's a third-party app totally unrelated to Facebook. Here, app A and the website have the same security principles because they are all from Facebook. So we think it is okay for app A to get cookies from facebook.com, but app B have no relation with Facebook and they have different security principles. So it is suspicious for app B to do such behavior. Our observation here is that, therefore, that it is risky when the security principles are crossed. Based on these observations, we give the following definitions. We can see in the example that when the web resource is manipulated, there are two security principles involved. The first is the web principle, which represents the manipulated web resource, marked as PW. And the second is the app principle, which represents the manipulating code, marked as PA. And we then define cross-principal manipulation, short as XPM, when web principle and app principle are not the same. And we think that XPMs may be risky to the web resources. And our target in this paper is to measure XPMs in real-world apps. To find XPMs in real-world applications, we can do this in 3 steps intuitively. The first, we can locate all manipulations from the code, and the second, we identify web principal and app principal. And the third step, we determine whether web principal and app principal are the same. And if they are not, we regard it as a XPM. However, in reality, these steps is non-trivial because we must solve at least several challenges. The first challenge is to accurately identify app principals. It is hard to directly compare to identify app principals because there are multiple security principles exist in the app, including the host app itself and several third-party libraries. Concerning the previous case, it is also possible that the manipulating code is from Facebook's SDK. So that is integrated into the app chat to us as a library. So in this case, it is not a XPM because Facebook's official SDK and Facebook.com all belong to Facebook. To solve this problem, we first identify third-party libraries reliably and accurately. And then if we find the manipulating code is from a third-party library, we can use the library name as the app principal. And if they are not from libraries but the host app, we can use the host app's meta-info, such as the app ID, the app name, and developer's information as the app principal. Our library identification algorithm is based on a Merkle tree code signature, and we will omit this due to time limitation, and please refer to our paper for more details. The second challenge is to accurately determine whether app principal and web principal are the same. The challenge lies in that there are semantic gaps between web principal and app principal. Again, considering the previous case, how can we be sure that chat2us and Facebook are not from the same security principal? Is it possible that chat2us is actually a sub-company of Facebook, just like Google and YouTube? And also there are abbreviations. For example, FB is short for Facebook. Our observation is that we can ask the search engine to bridge the semantic gaps. For example, when we search Facebook and FB respectively in Google, we can find that they have more than 80% similarity in their searching results. And therefore, we developed a searching-based classifier that asks search engine for results and normalize the search results into 2 vectors W and A using bag-of-birds model. And we then calculate the similarities between these 2 vectors, and if that similarity distance is larger than a predefined threshold, we think it is XPM. Okay, based on the above insights, we design and implement XPMChecker to automatically find XPM in real-world mobile apps. It contains 3 modules, and first, it accepts APK as the input, and with the help of predefined API models, it extracts manipulation information and save them into a database. And the second step utilizes the whole database and identify web principal and app principal for each record. And the last step utilizes the search engine knowledge to give a final result on whether it is XPM or not. Our implementation is based on Suite and FlowJoid framework, and with our customized inter-procedural control flow graph and API-specific data flow analysis. You can refer to our paper for more technical details of the static analysis. We then evaluate XPMChecker on a dataset with more than 84,000 apps downloaded from Google Play during July 2017. These apps are selected with more than 5,000 installations across 48 categories. And our evaluation shows that XPMChecker have both good performance and effectiveness for us to conduct our empirical study. More specifically, XPMChecker is able to successfully analyze more than 95% of all apps, and with 10 seconds per app. And with 200 manually labeled ground truths, its classifier can achieve about 99% precision and 98% recall. Okay, we then share some findings and insights by our empirical study. First, we studied the prevalence of XPM, and we found that XPMs are really very popular in real-world applications. About 5% of all apps contain XPMs, and we listed the details in the table, and we can find that nearly half of all web resource manipulations are actually cross-principal. And we then studied the location of XPMs, and we found that a large part of XPMs are from libraries. More than 63% of XPMs originate from 88 libraries in our dataset. This brings us reflections on current defensive work that consider the app as a single principle. So this kind of idea is not fine-grained enough nor accurate, because our results show that a large part of the manipulations are from libraries. What's more, we further studied the intents of XPMs, and we found that more than 90% of XPMs provide normal utilities. For example, they may inject JavaScript into the web views to custom web services to improve user experience. Examples are that they may add navigation controls to the web view, because we know that the web view is in Android and iOS do not have navigation controls. They cannot have the user interface of going back and going forward. So some apps just inject JavaScript to add these functions. Or we find that many apps use JavaScript to customize Google Cloud Print to reduce certain procedures, so to improve user experience. And also there are some apps that monitor the web addresses to invoke local apps according to the corresponding web pages. And most importantly, we are able to confirm malicious XPMs in real world for the first time. We found 22 malicious XPMs in 21 apps with up to 130 million installations on Google Play. We report this to Google, and the malicious intents are all removed. And by inspecting the iOS counterparts of the 21 apps, we confirm 4 of them have malicious XPMs on iOS users. We then classify the malicious intents into 3 categories. Category 1 have 2 apps and that impersonate legitimate relying party in OAuth, and there are 6 apps in category 2 that steal user credentials, and 14 apps steal and abuse cookies. We will show one case for each category. Okay, case 1 is an app named InstaView that impersonates Tinder in Instagram OAuth. Tinder here is a very popular app, in this case the victim app. And this app InstaView that uses Tinder's client ID to do OAuth, and when the OAuth server responds the access token for Tinder, it just intercepts the web address to extract the access token, and then it uses the access token to access users' sensitive information. The second case is an app called Empirical that steals users' Google account credentials. When the user logs into their Google account, this app will inject a malicious JavaScript to extract the email and password of the users. And the third case is an app called Chat to Us. It's a very popular chatting app with more than 10 million installations on Google Play. It steals Facebook cookies and abuses the cookies to collect sensitive user information and send spams. We can see in the figure that the code, it uses cookiemanager.getCookie to get cookies from Facebook and attach that cookie to access users' homepage to access sensitive information, and then send spams to each of the user's friends. Given the fact that such malicious XPMs can bring severe security challenges for the web service providers, we then studied the targets of XPM and the awareness of the targets. We found that more than 70% of XPM's targets top popular web services such as Google, Facebook, YouTube, and Twitter, etc. We then do experiments on these web servers, and unfortunately we found that most of them are unaware of such risks. All the above providers except Google allow sensitive web services such as account login and OAuth to be loaded into web views of any apps. Google announced in August 2016 that OAuth is no longer allowed in web view, but its countermeasure is easily to be bypassed. It only uses the user agent HTTP header to determine whether the request is from web view or not, but that HTTP header can be easily modified by the host apps, so its countermeasure can be bypassed easily. To conclude this paper, we proposed a measurement tool called XPMChecker to automatically find cross-principal manipulation in real-world applications. And we conduct the first large-scale empirical study on XPMs in real world. And our empirical findings can help a better understanding of the threat and development of countermeasures. And also, we confirm malicious app-to-web attacks on both Android and iOS that already affect a large number of devices. To facilitate the community to understand this problem, we released our dataset at the XPMChecker website. And that's all. Thank you. Please feel free.
Do you have any question? I have a few questions for you. It's more like clarification. What if I access, for example, google.com inside the web view in the application?
Yes.
Is there my default cookie in my default browser will be sent to the server?
I'm sorry?
If I access one of the web pages inside the web view,
yes.
Are you guys sending a cookie of my default web browser, or they have a separate section for the web view?
Because most of the web services do not know they are loaded into a web view or not, so it generally behaves as the normal use case. In this case, when users do OAuth to Facebook OAuth in the web view, the Facebook server will think that, okay, the user is doing OAuth now, but maybe he will use OAuth to allow another app. So why not I just send the cookies to the user, so next time the user won't need to input his password.
Actually, my question is more about to web view and the default browser in user in Android. Are Are they sharing the default cookie?
I'm sorry for the misunderstanding. And currently on Android, in one app, if there are two WebView instances, they share the same cookie storage. So when you use get cookie, you can get cookies of the web domains even loaded in another web instance.
Okay, let me ask once more. If I access google.com 2 times in the web view,
yes.
Are they gonna share the cookie between them?
Yes.
Or whenever I launch the web view, they're gonna create a new session and store those cookies.
Yes, of course, they will share the cookies. But if your website sets the cookies expiration time very small, it may be expired.
Let me ask a last question.
Okay, thank you.
It seems the boundary between features and malicious behavior is kind of fuzzy in this work. To me, in my perspective, the problem in general should be like phishing.
Okay.
If we remove, or can you think of any countermeasure against this kind of problem?
Actually, currently we think it is very hard for both the web servers and OS to actually decide whether the content is loaded into a web view or not. So sure, there are countermeasures, but there are no perfect solutions yet, I think.
So what about we using, in the iframe space, there's a special HTTP header that the developer can decide whether they want to be inside the iframe or not. Can you apply the similar approach in this case?
Because in our thread module, the host app can control the whole web view, so such kind of countermeasure can be bypassed by the host app.
Okay, thanks our speaker once more.